You're listening to the Knowledge Archives podcast. Welcome to the Knowledge Archives podcast. We're a group of students on a mission to learn from as many different disciplines of knowledge as possible. I'm your host, Madhav Malhotra, and today I'm lucky to be joined by Dr. Christian Schubert, a professor of physics at the Institute for Physics and Mathematics at the Michocan University in Mexico. His work integrates mathematical disciplines with fields of quantum physics, especially in the areas of string theory and quantum electrodynamics. I'm very excited to learn more about these specialized areas and their unique history today. So thank you for joining me today. I really appreciate you taking the time, and I'm very much looking forward to learning more about this incredibly specialized area of physics. But first of all, I'd love to just hear a little bit about your story, maybe a quick introduction and how you got started with even just discovering this incredible area of work.
Well, all right. I'm Christian Schubert. I'm a professor at the University of Michocan, the third largest Mexican state university. And I'm actually German. I studied mathematics in the city of Regensburg and physics. I did my PhD in physics and also my habilitation. Originally, my interest in childhood was really more philosophy, languages. It was actually my high school teacher who got me interested in physics. Sometimes teachers can be very important. And since I had a strong grounding in mathematics, I specialized in mathematical physics, particularly in computational methods. So right now I have a team in Mexico where we try to push the limits of what is calculable, particularly in quantum electrodynamics. Quantum electrodynamics is a theory that is 80 years old, but computationally, we still are not where we would like to be. We have to do years of work sometimes to calculate just one more term in a series of perturbation. And I have specialized a bit on using methods from string theory to improve on calculations in quantum field theory, particularly in strong field quantum electrodynamics, which is now becoming a hot topic because of the very strong lasers that are being built all over the world right now. Yeah, that's basically what I'm doing. I am a mathematical physicist with a strong computational interest, mainly centered in quantum field theory, but I'm also branching out into string theory, particle physics, laser physics.
Mm-hmm. And when it comes to this background, I know that, as you said, these theories have a long, decades-long background in having the theory be developed over time. But for most people, these are things that they've never even heard of when it comes to the general public. So I thought it would be great, first of all, to just learn about the historical developments of this field. And I know you have decades of experience with quantum electrodynamics in particular. So I'd love to ask you about, first of all, how this theory kind of got started and the developments that you've seen in how it is being studied and applied over the course of your career.
Well, quantum electrodynamics followed very logically from quantum mechanics. The moment when experiments reached sufficiently high energies. The thing is that nowadays, when we talk about quantum physics or quantum mechanics, we usually mean non-relativistic quantum mechanics. That is when particles are still conserved. Like most of chemistry, for example, is essentially atomic physics, where you just have electrons moving around, but you don't have electrons being created or destroyed. The moment you have energies where you can actually create electrons, then things become vastly more complicated. In fact, quantum electrodynamics was developed in the 30s, and it was considered so ugly that most people didn't want to apply it, but thought we have to rather improve that theory. That can't be. the true theory, because there were infinities all over the place. Yeah? It is in fact only in the late 40s that people understood how to remove these infinities in a physically meaningful way. Yeah? And then quantum electrodynamics became basically the template for all other theories. Like today's standard model of elementary particle physics basically follows quantum electrodynamics. Yeah? Just you have many more symmetries, you have more degrees of freedom, you have more interactions, but essentially the structure is still like in quantum electrodynamics. And it's a field that has developed hugely. Every time I give quantum field theory or quantum electrodynamics, I feel, what do I do in one semester? Strictly speaking, it would need at least 8 semesters to teach what students really should know. Yeah? And it becomes much worse than string theory. Yeah? Like string theory is our only known mathematical generalization of quantum field theory. And it's vastly more complicated. Yeah? And in fact, quantum field theory is something like any intelligent person can study and learn. But string theory, I would recommend only for people who have a real knack for mathematics. Yeah? In fact, in string theory, you have to be able to acquire very advanced mathematical concepts in a short time. Yeah? Otherwise, you won't be happy working in that field. Yeah?
Mm-hmm. And when it comes to this kind of difficulty, I know that I was talking about how a bunch of people might not even have ever heard of these fields, but especially when it comes to people breaking into these fields, as you said, there's such a huge amount of background concepts to build in not just physical theories, but foundational mathematics that you need to understand before you can talk about these theories. And when it comes to this barrier to entry to, say, new students entering into the field, could you briefly describe your personal experiences with this as a student, but then also when you do see, say, new researchers coming into this field, do you see that oftentimes the area is understudied because there aren't as many people who have dedicated the enormous amount of time that it takes to enter the field?
Well, I wouldn't say that we don't have enough people working in the field. In fact, typically, I have taught in Germany and in the US and in Mexico, and it's everywhere the same. I see that the best students usually tend to go into high energy physics. They're attracted by mathematical physics. And there was a time when string theory was a huge attraction. I was a student in the late 80s when string theory had a real boom because it looked like we have a chance now of getting a really unique final theory. And also, there are quite a number of books in popular science, which I think are really accessible to intelligent laypersons. And I know people who are not physicists, but they have an interest in this. So I would not say that quantum field theory, string theory are not having an effect on general culture. Yeah? The problem is that now string theory had a big boom, and then unfortunately it fizzled out a little bit because it has unfortunately not enough predictability. It's in a way funny that string theory we like because it generalizes quantum field theory, but it has the opposite problems of quantum field theory. In quantum field theory, you have a very restrictive framework. Yeah? In fact, this procedure, which we call renormalizability, to remove infinities from the theory, is very restrictive. And in fact, it leaves you a finite number of possibilities. And in fact, the standard model of elementary particle physics basically uses all of them. Yeah? In string theory, we have the problem that you don't have enough restrictions. Yeah? There are billions and billions of possible theories. Yeah? And basically right now, nobody believes that we will be able to choose. So what people are trying now is to get some generic ideas from string theory. Yeah? Like string theory suggests, for example, that there could be milli-charged particles, so particles that are like electrons, but have a much smaller charge. Yeah? So we have some hints which you can give to experimentalists. Look for particles with a very small charge. Yeah? But in general, there's a feeling that string theory has a disappointment. And now theoretical physics basically does not have this big project anymore. Yeah? So we are a bit dispersed right now. Yeah?
Mm-hmm. And when it comes to these problems with the limitations of these different theories, and especially, I know that reading some of your research papers in the past, you've studied how these different theories intermesh together, where are the areas where they are each different and where we have to choose between, say, one or the other, essentially. What are some of the areas of studies in these different theories, in string theory and quantum electrodynamics, where we have some of the largest limitations in each of them and some of the largest problems in being able to combine the two to analyze like what is actually true in the world?
Well, quantum field theory has one big limitation, that is that we do not know how to combine it with gravity. And that problem string theory has solved. In fact, that was probably the biggest success of string theory, that it very naturally combines gravity with the other three interactions. Yeah? And also string theory has also freed us a little bit from this idea that physics has to be in 4 dimensions. Yeah? Like even before string theories have been Kaluza-Klein theories where you put some additional dimensions. But it's really string theories that made us kind of feel like the fact that we are seeing 4 dimensions is kind of an illusion, and there are other dimensions which are just kind of hidden. Yeah? There are various mechanisms how you can explain that there is a dimension that you actually can't easily see. Yeah? But then again, you run into a problem. The moment you feel like physics could be in any dimension, how do you explain that we see precisely 4 dimensions? Yeah? That is one of the a box which you open and you can't close it anymore. Yeah? It's philosophically not nice to have all these open questions which you can never answer. Yeah?
Mm-hmm. I think that it's really important to notice these areas where we currently have a lot of unanswered questions, because when we look at the history of science and physics in particular, it wasn't so long ago that we still had these few key areas that people were wondering about, thinking of physics. We've figured out everything. We have all of the Newtonian models that we need, and there are just these few key areas that people were unsure about. But then after that came so much complexity that we're still trying to figure out now. And based on that, I just wanted to ask you, when it comes to the progression of this field, what do you think are some of the questions like that when it comes to where areas might be understudied, where we still have the largest questions that maybe people aren't focusing as much on, and you see that in the future you'll have more people working and studying these areas?
Well, right now, I think most people would agree that most important problem in physics is to understand the nature of dark matter. But it is a problem which is very hard to attack in a direct way. Yeah? There are just too many possibilities. Yeah? Like even if you would now have 10,000 more competent physicists working on that problem, there's no guarantee that they soon would come up with something. Yeah? It is a kind of problem which might be solved only in an indirect way, like somebody constructs a new model, and this new model just needs a particle with a certain mass, and then it just fits the astronomical observations. Yeah? So it is really hard to tell people what should you work on? Yeah, what is certainly a good idea is to work on strong field quantum electrodynamics, because we have all these super lasers coming up, like Eli in Europe, and in Korea they have a very strong laser now. In China and Russia, they are already planning extremely strong lasers. So a lot of theorists will be needed. Yeah. So anybody who wants to, well, I'm sending, in fact, some of my students into this direction. Yeah. In fact, it has been giving a boom to quantum electrodynamics. Yeah. Another interesting application now of quantum field theory is on condensed matter. For example, you have probably heard of graphene, which is a material that is extremely thin and can be treated almost like a two-dimensional structure. And it turned out that in some approximation, actually one can apply quantum electrodynamics to it. Even so, it is a non-relativistic system, but there are relativistic methods that work in a certain approximation. So next few years, we will see a lot of activities there.
Mm-hmm.
On the other hand, classical particle physics, high energy physics, dispersion theory, that is now a political question. Will we still have one more particle accelerator? You probably heard about a linear accelerator, which one would like to build, but which might be the last one, because there are physical reasons why, if you want to go to higher energies, you must build ever larger accelerators. Yeah. For a linear accelerators, the restriction is very obvious, because you have to accelerate a particle to a very large energy, so you need a long distance to do that. In a circular accelerator, you have the problem that the particles will radiate if the radius is not very large. So generally, there's a belief that there will be probably a linear accelerator, but after that might be the end of it. So this is something students must have in mind when they specialize. Yeah.
Mm-hmm. And I think it's really important for future researchers also to consider the last area of questions which I had for you, which were more so around your personal experience working in this discipline, and especially regarding one of the things that you just said was how to apply this area of work to more and more things, like, say, with the chemistry of graphene and different quantum properties, etc. And I've also been seeing how quantum mechanics in general, not just in quantum electrodynamics, a lot of the not just physical theories, but even the statistical methods in mathematics used, say, with analyzing the probability of where an electron might be located. Even these simple things have started to be brought over in different areas, from, say, the statistical methods being applied to studies in psychology was a recent thing I found, or where we were talking to other researchers about optics and, say, quantum microscopy, etc. Regarding these interdisciplinary areas of work, have you found that in your discipline, oftentimes we have these theories that are, say, undiscovered by other scientists who might be able to integrate them in other ways? Or do you find that there is a lot of interdisciplinary work between physicists and people from other disciplines?
Well, I must say, I myself have not done a lot of interdisciplinary work. I have sometimes worked with my wife, who's actually a physical chemist and working on plant physiology, and sometimes have helped her calculating stuff there. But generally, it is like the methods that we develop in field theory and in quantum mechanics can sometimes be applied in unforeseen ways. Like, I have a colleague who actually now he works on financial markets, and he says, well, he has a huge advantage compared to other people doing computational forecasts of the financial markets, because his grounding in statistical physics allows him to see certain things. Like, he told me, yeah, my colleagues They don't understand what is actually a zero mode, what is a collective mode. I look at their data and I see things they have no chance of seeing. Yeah? It is true that the methods that we use in quantum field theory and in statistical physics, they are very universally applicable. Yeah?
Mm-hmm. And this brings me to my last question, which is if you were to give some advice to people entering theoretical quantum physics, perhaps in quantum electrodynamics or quantum mechanics in general, what are these kinds of tools that you would advise people, say, for instance, to build their mathematical intuition behind statistics, or even just more broadly consider different types of epistemological theories or consider research methodologies or other more general tools that they might be able to use in their career?
Well, my general advice would be to learn many different methods, not to specialize too early. I have seen biophysicists who say, well, I will never need even complex analysis. Why should I learn that? That I would not recommend to a student. Yeah. Even if you want to do applied physics, try to get all the theoretical tools. Yeah. Because later in life, you might find it very hard to acquire them. Yeah.
Well, I think that's a really practical bit of advice to be able to explore different options that you might literally be blind to, as you were saying with the example of your friend, and that you might just not even be able to recognize what's in front of your eyes without knowing these different theories. So I think that's a very practical note to end off on. And I finally just wanted to ask if someone were interested to learn more about your work, where might they go?
In fact, in our university, we have a program for attracting foreigners, which is actually quite generous. We do not have study fees, and we provide a PhD fellowship that is actually quite generous for Mexican cost of living. Of course, right now with the crisis, all this is basically being put on hold. But we, at some point of time, we have had students from 20 countries, in fact, in our institute.
So I'll be sure to perhaps add a link to learn more about that for anyone who's interested. But thank you again for taking the time to explain all the way from the historical development of this field to kind of what's next and what people need to do to explore some of the large questions that we have here. I really appreciate all of this insight.
Thank you for the invitation.